So here's a summary of where we were last time. We're considering some class of antiferromagnets. These are spins on some lattice with spin orange S, angular momentum S. And today, in fact, we'll consider some general set of lattice, but with translation invariance. So I'll just do some general coupling Jij. And the way we proceed to solve this problem is by using the Schwinger fermion representation. We decompose the spin in terms of these spin-a-half bosons. There's two of them, S up and S down. And there's a constraint on every side that the number of the Schwinger boson is always an integer. So we made an integer in this half case, so this would be 1. And then I showed you through a series of manipulations that you could read out the path integral of this problem as a path integral in terms of two auxiliary fields that we're going to play with today. One is this bond field, or every bond is a Qij field, which is a complex number, which is conjugate to this particular combination of the Schwinger bosons. And you can just see that this is an operator that annihilates a singlet pair. So you have a valence bond of the spins, up, down, minus, down, up. And if there's a valence bond, it's annihilated by this operator. So you can think of Qij as just the valence bond operator, which is measuring exactly how these valence bonds are fluctuating, and also the relative phases between different arrangements of the valence bonds. And then we also had to introduce a Lagrange multiplier to impose this constraint. Okay, so then we're going to get some very complicated action, which is hard to write down in general, but we're going to study it today. And one of its most important properties is invariance under a gauge transformation. So the first thing we did was just to take this action and look for saddle points that were spatially uniform. And people have done that for many, many lattices. And so today we're going to focus on the triangular lattice. You can get some solution of the Q's, which we'll call Q bar and lambda bar. And then about the saddle point, if you look for the Hamiltonian for the original S bosons, then after a Bogoliubov transformation, you got another boson, gamma alpha, which was an eigen operator of the Hamiltonian. And this gamma alpha created a bosonic excitation that had an energy gap and that carried spin-a-half. So this is in some sense already quite a exciting discovery here. You've got an excitation that carries spin-a-half. So it's a fractionalized excitation. And it's very surprising even though the spins here may be spin-a-half, even though this orange S may be a half, we haven't yet met any other system which has an excitation which has spin-a-half and also charge 0. So the electron, of course, is an excitation in a Fermi liquid that carries spin-a-half and charge 1. But here we're finding kind of a violation of the usual spin statistics relation. So you have a half integer excitation, which has 0 charge. This doesn't carry any charge at all. We haven't even mentioned the charge of the electron. And that's surprising even for half integer spin antiferromagnets, because here this is measuring a difference in excitations, differences in spin. So you have the ground state. Now the ground state may have spin 0 or spin-a-half, depending on whether it's an even or odd number of spin-a-halves in the original Hamiltonian on the lattice. But the differences between energy levels is always an integer spin. So if you had an odd number of spins, the energy levels would have spin 1 half, 3 halves, 5 halves, and so on, all of them. So all excitations will have integer spin. And so surprisingly, we found an excitation which has half integer spin. So that's quite remarkable. And of course, the only way this can happen in any finite system is these are created in pairs. You can create pairs of them and separate them out to infinity. And so these, sometimes it's called spin charge separation. You've got a half integer spin with no charge. And spin waves in an antiferromagnet or spin waves in a ferromagnet all carry integer spin. So there's no problem getting integer spin with zero charge. Paramagnons, all these objects have integer spin and no charge. But this is the first time we met an object that has half integer spin and no charge. And in this matter, we call this the spin-off. So that's the word I'm often going to use. There's also a connection to the toric code, where this is the analog of what we call the E particle. So this is a bosonic spin-off. All right. So that's already a nice story, but we now still have to do this path integral, which is what we're going to turn to today. Okay, any questions? Yeah.
There's no claim that this is a superconductor as it stands, right?
Oh, no, not at all.
It would require doping or something.
That's right. That's right. Yeah, if you dope this and you have motion of charge, then this particular pairing could combine with other. You also have to end up condensing something that carries charge, and the combination can lead to superconductivity. Yeah. I mean, and that in some sense is, in broad terms, Anderson's original idea that the singlet bonds in a liquid like this would turn into Cooper pairs once you allow them to actually move around and carry charge. Any other questions on Zoom? Okay, so let's now forge ahead and try to do this path integral. In general, that's a very complicated task. And in some cases, that's still a topic of current research. But for a particular case, you can make a lot of progress by a certain set of very reasonable arguments which give us greater understanding of the structure of the space. So the first thing you can do is look at perturbative fluctuations. So this means you take a Q from Q bar and you change it a little bit. And you take lambda from lambda bar and you change it a little bit. Okay, so we looked at that last time towards the end of last lecture. And that's already a complicated task, but we gave rather general arguments that on certain lattices, in particular on the triangle lattice, these fluctuations are also gapped. So they don't give you any new very low energy excitations. They'll give you some other particles that will carry spin zero. And in general, you would think those particles would probably decay into a pair of the spin-ons. So there's nothing fundamentally new really there. So we looked rather safe and maybe have indeed found a theory in which there is spin charge separation. Spin a half excitation with zero charge. Okay, but that's not sufficient. You really have to do better. You also have to look at non-perturbative corrections. So we're going to go to beyond perturbation theory. We have to look at new saddle points, and we have to sum over all of them. And we have to make sure that summation doesn't lead to any fundamental instability. In fact, so that's the task we're going to embark on today. And we'll find that's indeed the case, that this thing looks to be non-perturbatively stable. And one of the outputs of that, we will also discover when it does become unstable. So eventually, there'll be a phase transition to another phase of matter, where these fractionalized excitation, the spin-ons, get confined. So we'll have a deconfinement to confinement transition. And the confining phase will then, in some sense, be a boring phase because it will not have any half-integer spin excitations. So we want to describe that too, and see if there's any general constraints, and then what happens to this phase that we're discovering here. Okay, so the first step there is to look for new saddle points.
Sorry.
Yes.
Did you have motivation for selecting this particular saddle point? Was it just spatial uniformity or?
Well, yeah, I mean, I think, yeah, you can certainly look for non-uniform saddle points. They generally will have higher energy, right? But we're going to pick out a particular set of spatially non-uniform saddle points soon, because as you'll see, they have the potential in them to eventually destroy this particular saddle point, this particular phase. But there'll be a finite range of couplings that we don't, and that's something we can argue pretty strongly. Okay, so to understand the structure of other saddle points, in fact, the simplest place they first appear is on a torus. So take the system and put it on a torus. Okay. Here's a torus, a very big torus. And so it has circumferences, which I'm going to call L. That's the length of the circumference of a torus. Really, I should draw it in a plane. It's a plane here, and I'm identifying these boundary conditions. So this edge is the same as that edge, this edge is the same as that edge. And we put, solve the equations in this plane with periodic boundary conditions. That's really all we're doing. Okay, so we found in the infinite plane that the lowest energy saddle point was Q equals Q bar, with some orientation of the arrows on a given triangle and so on. Now we just take that solution and put it on a torus. And now my claim is that there is another saddle point, which has almost, in fact, 3 other saddle points have almost exactly the same energy. To see that, let's first write down schematically of the structure of S. And I won't even ignore, I'll ignore lambda for now. So S of Q, has various terms, but the kind of terms you're going to need, well, first of all, there could be some potential, which depends on the Q on a given length. And there could be some time derivative terms like this. In fact, I'm going to work in a gauge where I fix lambda to be time independent. I can always choose my rho so that lambda is time independent. And then this is also gauge invariant. So I'll only be thinking about time independent gauge transformations. And then I can get various terms, sum over loops with some coefficient, CL, or product on Qij belonging to a loop. So it will be Q star, things like this. Now, one important feature of this theory, so where have we got all these terms? Well, all these terms come from, in a sense, from doing the path integral over the S. I do the path integral over the S, and I put in various source terms for Q and Q star, and I just integrate over the S, and I'll generate some effective potential for Q. Now, the most important property of the S is that they have an energy gap. One of the important properties. There's some energy gap here. So as these look bigger and bigger, become bigger and bigger, I can see that the C sub L of a loop of length L, this is a different L, let me call it. Okay. C sub L will decay exponentially, roughly, where this delta is the energy gap. And there's some velocity which is about 1. Okay, so the bigger this loops become, because the things we're integrating out are gapped, the coefficients of these loops become smaller and smaller and smaller. Okay, so that's a very important quantity that we need. Okay, so now let me show you another saddle point on the torus, which has almost the same energy as the infinite lattice saddle point we found. Well, all of them are slightly different because they're not torus, actually. So I'm going to draw a cut here. Let me choose a different color. Okay, so this is some cut through the lattice. I mean, there's actually a triangle lattice here. Here, let me blow it up. And then I draw a cut through the lattice, which cuts the bonds in any path I want, but it encircles the torus. And then I do the following for every Qij that cuts the bond. So there's some Qij here. So Q, this is I, this is side J. If it cuts the bond, then I'm going to say that Qij goes to Q bar, the infinite lattice value, times -1. I'm going to flip the sign of the Qij on every Qij that cuts this orange line. Okay. So now why am I doing this strange thing? Well, the first thing, important thing you should now know is that for almost all loops, this has absolutely no effect. Because if I take any loop here, L, if I take any loop on the lattice, it's going to cross the dotted line an even number of times. It's going to cross it once here and once there. So for essentially every term in here, there's no change in it. It doesn't even know the branch cut is there because there's a -1 here and a -1 there. So in fact, even though it looks like this branch cut is visible and it's broken translational symmetry or broken the full symmetry of the torus, it hasn't. It's in fact as if it's not there, at least locally, because these loops don't change at all. So we expect essentially the absolute value of Q to not change, at least so far. But there's one special loop, or one second class of loops where things do change. And that's a loop that goes around the cycle of the torus. There's a loop that goes like this, around the cycle of the torus, comes back the other side. And what you notice is that it only cuts this dashed line at one point. Okay. So this state is a different state. It's not the same saddle point, because there's a gauge invariant object that goes around the other cycle of the torus, which does change. It flips sign. But what is the contribution of this particular loop? Well, that's of length L, script L. And so it's exponentially small than L. The C sub L, the coefficient here, is exponentially small. So therefore, if you're willing to ignore these exponentials, which can be made arbitrarily small, as L goes to, as script L goes to infinity, then this saddle point essentially is essentially the same, independent of whether this dash cut is there or not. Yeah.
Both cycles have length L's?
Yeah, order L. Of course, you can make them different.
Yeah.
Right, thank you. Okay, so that's the main argument. And so you can see, so now I've got at least two saddle points. There's a saddle point with no cut, and then there's this saddle point with one cut. It's a completely different saddle point because there is an observable which is different, which is the cycle the loop around the other cycle of the torus. And the difference in energy is exponentially small. So what you can say is that the value of Q bar will be the value of Q bar in the infinite lattice. If you re-minimize the value of Q bar in this particular expansion, plus terms which are of order e to the minus delta L. So we found another, essentially a ground state, apart from an exponentially small term, which will generically appear in this type of saddle point. And of course, you can put the cut on the other cycle of the torus. You can reverse the role of these two cycles. You can put the cut on the other side and take this Wilson loop, as it's called, on this side. So in the end, you end up with a total of 4 nearly degenerate ground states. Okay, so that's a very important property here, that on a torus, this particular spin liquid state has a 4-fold degeneracy. Okay. Any questions? Okay, so that's really quite a remarkable observation. And these kinds of degeneracies were first noticed, at least in condensed matter, in the fractional quantum Hall states of Laughlin. If you put them on a torus, they have similar degeneracies. Not the same numbers, but now they're appearing here in this simple spin model in zero magnetic field with time reversal symmetry. Okay. Questions? All right, so now degeneracies of ground states by themselves are not that new. If I took an ordinary Ising metal or ferromagnet with low continuous symmetry, then you can imagine there are 2 ground states on a torus, one with all spins up and the other with all spins down. But the difference between that and this is, in that case, you can do a local measurement. You can look at the spins and see how they're up or down, and you can decide, well, they're all up, and you know which ground state you're in. Here, the important point is that there's a 4-fold degeneracy on the ground states. On the torus, and you require non-local measurements, very specific non-local measurements to distinguish them. So that's the really interesting and important thing here. All the small loops have no difference at all. It's only if you just happen to take a loop that goes all the way around the system, an extremely long, unlikely event, they were just randomly making loops in a very big system. Only those can tell you what the different states are. So that's something we haven't met in any previous system that we've studied so far. This degeneracy, which is not associated with any local observation or with any broken symmetry.
The true ground state's going to be symmetric superposition of the 4 states.
Yeah, so in general, what would happen would be something very complicated. Is there'll be 4 states, and there'll be some linear combination of the simple states I've shown here. And exactly what linear combination there are will depend on various exponentially small terms in the Hamiltonian in this 4-fold subspace. So we are going to see a little bit of that when we get to the Gauge theory.
If we send the size of the torus to infinity, then
Yeah.
What happens to these others? They're still there, but the operator we need becomes more and more non-local. And I mean, if we make
These are, so, there's 4 states here.
so I'm just saying on the plane, do we still have a 4-fold degeneracy? Or
In the plane. Well, that's kind of a singular limit.
reflection sectors in it?
Yeah. So, I mean, in the plane, not strictly speaking, I mean, there will be could be edge contribution that I have to worry about. It depends on what's happening on the edge. But on a torus, there's always a 4-fold degeneracy for any size, as long as M is sufficiently large. And then there's a gap of order delta to all the other states. And this remains fixed. Okay, and precisely what linear combination you get in your energy eigenstates will entirely depend on all kinds of details and various matrix elements between these states, which in principle, you could evaluate from here by doing some rather complicated path intervals, which we can estimate what they are. Okay. I was going to say something else. All right, goodbye. Any other questions? All right. Right, so there's these non-local fourfold degenerate states. Oh yeah, I was just going to mention, of course, but the idea of quantum error correction and topologically protected quantum computing is that you manipulate the phases with precisely what these states are by manipulating and creating them in some linear combination. And what you're then assured of is that that particular linear combination that you happen to create of these four states is stable to all local perturbations, because all local perturbation act in the same way to all four states. So it's like a unit matrix in that subspace. So all the noise is just a unit matrix. Okay. Of course, these four are not enough for complete quantum computation. You need non-abelian states and so on, which people are trying to make.
Subir, how do you explicitly construct these states?
How do I? Why don't we wait to answer that, because it's rather complicated to state all this in this particular language. I'm going to simplify life for us and write down a simple gauge theory, Z2 gauge theory, and then we can see how we construct them in a much more easier way.
Okay, thank you.
Okay, so the existence of these four states and the existence of this invisible cut now should give us an idea of how to create another saddle point in the infinite lattice. So we're considering an infinite lattice now, and this will be a saddle point with higher energy. But what it's going to give us is another particle. In addition to the spin-ons, there will be another particle we're going to find. So what we do is we take an infinite lattice, and we take this cut, but have it terminate at one point. And really, if the lattice is finite, then it will probably terminate somewhere else. Okay. And you look for saddle points with this kind of cut. And in fact, my student Gauge has actually done this computation on the triangular lattice. They've taken some action like this and minimize it and look for saddle points like this. And now things are a bit more complicated than in the infinite lattice torus case. But one thing you can see that even with short loops, there are now some special loops we have to consider. If I take a loop like this, there's no change whatsoever in the energy for all these loops here. But there are a small set of loops for which there is a change. And then those are loops that go around the end of this thing, okay? So what you're going to find is that your Q bar of ij, and let me call it Q bar M meaning, I'll call this point M, this is going to be a particle called the M particle. So Q bar ij in the presence of an end will be equal to, approximately equal to Q bar that we found infinite lattice far from M. But it's not going to be equal to this. It's going to be different, take some set of values that you have to figure out on a computer. But anyway, it's not going to be equal to this. Oh, sorry, that's not exactly right. Or not exactly equal. And -1 to the number of cuts. Whether it cuts this line or not, a given Qij. If it cuts it, it's 1, and if it doesn't cut it, it's 0. So there's a change in the phase factor. But it's not equal to this, so this is close to M. Far from M, excuse me. But it's not equal, even the modulus of this in the presence of M is not equal to Q bar infinite. Close to M. So there's some region here in which there's many of these terms here are going to be different. Okay, but there's a small number of them, and since these couplings decay exponentially as you make those bigger and bigger, you can add over all of them, you'll get some finite energy. So this particular region will have a finite energy cost. Okay. But this is still a stable saddle point with a slightly higher energy cost. There's, in fact, an infinite number of them because you can now move this in anywhere in the lattice. So you got an infinite set of saddle points. And whenever you get an infinite set of saddle points marked by one position, that's what you call a particle. So you can now even imagine tunneling between these saddle points, and then this thing can move, acquire a mass, and it becomes the M particle. But we have, if you wish, a saddle point of that particle is stationary. It's got a, in time it's sitting there, and with some, you can evaluate this and figure out its energy for being localized at that point. Depends, if you think of the fact that the cube bars have changed over some finite region, you can think of that as a 0-point motion of the center of this particle. It's not really there because there's a finite region of which the cubes know about its existence. So we're undergoing some 0-point motion, but centered at this point. Okay. But one thing you do find when we do the numerical analysis of this, for example, that the change in this region, is in the magnitude, but the Q's never become complex. I mean, they could have become complex, but they don't. And so this particular saddle point is fully time reversal invariant. So now I'm going to make a few statements that some of you may find a bit mysterious. So these have to do with the connection of this particular description to the field theory of a U1 gauge field coupled to a charge 2 Higgs field. Now that particular theory also has similar saddle points. These are the Nielsen-Niemeyer vortices, or called the Abrikosov vortices in theory of superconductors. And so those vortices have flux, which is half a flux quantum. But in fact, those vortices break time reversal. Any given vortex, either plus half or minus a half, or in fact, any half integer. There's an infinite set of such vortices, and any given one of them does break time reversal. So it is in that sense, the mapping to charge 2 Higgs field plus compact U1 gauge theory is not, but it's correct, but it's a little subtle. What you have to realize there is that because the theory also has monopoles, like a plus half flux vortex is the same as a minus half flux vortex because a monopole can tunnel between them. So once you include monopole, you restore the time reversal symmetry, and you get these vortices, Wisons, they often call it condensed matter, or M particle in the toric core, which just have the feature that there's an end to this branch current. Yes.
Do numerics show a large, or how big is the region where Q is very small? I guess.
It's of order 1 over delta. Yeah. So the bigger the gap, the smaller the region. Yeah. Okay, so for now, let's just consider this particle to be stationary. We're going to talk about how this particle moves next. It also has some very subtle features in its motion. But let's imagine we created one of these particles by a very clever experiment, and we can look at it. So one way we can look at it is by using the S particles. So we come in and do a different experiment, and we create an S particle somewhere far away. We create an S particle here. And we're going to take the S particle very slowly by trap it in some very gentle potential, and we very slowly move that around in a big loop like this. Okay, so I'm sitting way out here, and my experimentalist friend gives me 2 samples, and the experimenters tell me one sample has an M particle inside, the other one doesn't. So I do the same experiment very slowly of moving this S particle around. and bring it back. And when it comes back to the same point, I can measure the phase of the wave function to the process, to the initial wave function. So take it in a closed loop, bring it back to exactly the same point, and do exactly the same experiment in the two samples. And what I'll find is that there's a relative phase difference between the two, because in the sample with the M particle, I had to cross this cut. And when I cross the cut, I'll pick up a -1, because you can see the Qij, which is basically the object that moves the S particle from point to point. It's got two daggers in it, but that's not a big deal because the actual eigenmode, gamma, is a linear combination of S and S dagger. It's the only thing that's non-local that can move the S particle. And so you'll pick up a -1. So this particular calculation has actually also been done very carefully in the usual traditions of a very phase computation. And you can indeed show it's exactly -1. That's in, well, let me reference it to it in a paper written by my student, Eugene and Matthias Punk. Okay, so I have another very important conclusion that the S particle is the E particle, and the S boson, right? I should call it E. E and M are mutual semions. Okay, well, at least if I have a stationary M, then I can move an E around it, and I pick up a -1. And of course, here it doesn't matter whether I move clockwise or anti-clockwise, it's -1 and -1. But in the chiral spin liquids or the Laughlin states, it does matter. You get a different phase factor which way you move. It's a complex conjugate. And that's really the essential feature of time reversal symmetry breaking. Here, this is totally time reversal invariant. Okay. All right, any questions? Okay, so now let's consider a different set of saddle points which allow the M particle to move. Okay. And there's just one very important feature that I want to talk about, well, two further consequences. When the M particle becomes an actual particle with a finite mass, and that can move around. So for things to move, you have to consider time-dependent saddle points. Sometimes they're called instantons. But don't worry, I won't actually do any complicated instanton calculation. We can deduce everything we need to know and various orders of magnitude just by drawing a few pictures. Okay. But just to introduce what an instanton is, suppose I have the quantum mechanics of some particle, h is p squared over 2m, plus some potential v of x. Of course, I know how to solve this using usual quantum mechanics and Schrodinger's equation. But if I try to do this in path integrals, I can write this as a path integral of dx of exponential in imaginary time. Oh, 1/2 dx d tau squared plus v of x. I'll have all the signs right, I think I do. Okay. So now let's take a v of x of the following form. So this is our v of x. And then I look for saddle points of this. And I find one saddle point here and one saddle point here. So there's the two different positions in space. But as many people have shown, there's also other time-dependent saddle points, so-called instantons, go from here to there. And this gives you the tunneling between these two levels. So instantons. And I'll just say that describes tunneling. So we know quantum mechanically, there's when you have such a potential, there'll be two states. There'll be the symmetric and the anti-symmetric combination of these two states with some energy splitting. And this energy splitting is given by this instanton, the tunneling from here to there. So there's some very nice lecture notes by Sidney Coleman and many others, other books, where you can look up exactly how this is done. Since I'm not going to actually do such a calculation, this is really roughly all I need to know. Okay, so now I can do the similar thing here for the M particle. So I have my lattice. I want to draw a careful lattice. And if I look for instanton solutions, I will find solutions. That's just an assertion. I don't think anybody's actually checked this, where this object is hopping from point to point. Okay, so I have my M particle here. With a branch cut going out to infinity. And then I can find an instanton solution where it moves here. Okay. And then what will happen to the branch cut? Color, it will, somehow roughly be the same here, but it will move to that point. Okay. Or I can actually, even better, just draw it this way. Since it doesn't matter exactly where it is, let's say it moves there. Okay, so I'll get some tunneling amplitude. In this theory, we're pretty confident to be a real number, something very difficult to compute, but it's an instanton which allows this option to hop around. All right. So I got some number, and then I keep doing it. I make it hop around the loop. So now I had an M particle. So previously I was taking an E particle and moving it on a loop. Here I'm taking an M particle, not moving it around an E particle. I can do that too, and just moving it around one lattice site. And the reason I'm doing this is because this is a there's a very important property of the spin liquid that the ground state has finite density of matter. It has these bosons, S dagger S is 2s. And that finite density of matter does make a difference to the structure of the gauge fluctuations. So here, let's ask what happens when I move this particle back in a closed loop. All right. So when I come back, let's say I started here, and then I come back here. Now the final state physically is the same as the state I started with. So it's exactly what you would do to compute a Berry phase. Whenever you compute a Berry phase, you take something in a closed loop in parameter space. So we have some parameter space, and we've taken, which we localize this M particle, and I move it in a closed loop. And I come back to where I started.
The cut still goes around that.
Sorry?
But the cut still goes around that side.
Right. So, but in terms of gauge invariant objects, this is the same state. But the picture is not the same. So I have to do a gauge transformation to bring it back to the original gauge. Okay. So what is the gauge transformation that will get rid of the accident? Well, it's very simple. What I have to do is take all of these Qij and flip their sign. Okay, on the accident. But another way to say what is that gauge transformation is if I take the S particle over here, which is sitting in the ground state, you take S goes to minus S on that side. This is the S alpha. I flip S alpha, I do a gauge transformation where S alpha goes to minus S alpha. Then if you look back to the gauge transformation, all these Q's will flip side, and then this will be gone. Okay. All right. But the ground state has exactly 2 S bosons on each side. So this tells me that this process So the motion of M around a lattice site picks up a Berry phase I should get it back to sort in a bigger space. So important. Motion around the lattice site. Of -1 to the 2s. Because for each s boson, I pick up a factor of -1, and therefore there's a Berry phase where this incident picks up this M particle picks up a -1 as it tunnel around in the closed loop.
Sorry, I'm honestly confused, but
Yeah.
the position of the original branch cut is somewhat arbitrary, right?
Yes.
So why can't you rotate the branch cut as well? Why you rotate M? So
No, so when you do a Berry phase calculation, there's a certain gauge ambiguity in the Berry phase because the phase of the wave function is not well defined. So when Berry phase, to unambiguously define a gauge in Berry phase, you make a closed loop in parameter space where the Hamiltonian comes back to itself and is in the same gauge. And then there's a gauge invariant factor left over, which is the phase you picked up in that path. So as you go this loop, when you come back, the Hamiltonian has come back to itself up to a gauge transformation. So you have to do the gauge transformation to compute the gauge invariant contribution of Berry phase.
No, this I understand. I guess I was asking, like, why every time that you hop around this M, why are you just slightly modifying your branch cut rather than, for example, just rotating it so that at the end it comes back to the original one right away?
You can do that if you wanted,
And
but it will still be true. It'll still be true. You would be forced to do a gauge transformation on every site you circulate. In fact, in general, if you go around some big loop, you'll pick up a -1 to the number of sites times 2s that you enclose. I'm going to put this all in much more familiar terms for field theory and quantum field theory in a little while, maybe not today, but definitely by next lecture. But if you want, looking ahead, what we'll see is that this is described by an Eisengage theory, and this M particle is just a pi flux in the Eisengage theory. And the S particles have charge 1, Z2 charge 1. And so when you move a pi flux around the charge 1, you pick up a factor of -1, basically. All right. But this is, turns out to be really crucial, because these phase factors that are given by background density of matter for all these constraints that we've been talking about, like, half integers systems, you cannot have a trivial Mott insulator, the Luttinger theorem for Fermi surfaces. These are all in the same family of constraints, and this is in fact the simplest one of them. And you can see just by a few pictures, you can derive it.
Is it similar to the one the phase factor you derived before when an S goes around an M? Except that
No, this has to do with symmetry, that the number conservation of the S boson on each side. The other one was purely topology. I will rephrase this in terms of translational properties of Wilson lines and Tuft lines in a Z2 gauge theory, how they transform under translations. So it's very much associated with translations and U1 symmetry charge in this case. But you can also define it in the Z2 gauge theory in a simpler way. Whereas the other one, this is purely nothing to do with symmetry whatsoever. This phase factor will be present in any system, any Z2 gauge theory, any toric code. This doesn't exist in a toric code. You can't even define what S is in a toric code. Okay, I see some puzzle faces. Just wait a little bit. I think this will become clearer soon. Any questions online? I mean, another way to say there is a connection, if you wish, between this and this. Here we took an E particle around M, and here we took M around a lattice site. But the special feature of this antiferromagnet that each lattice site has an E particle in it.
Yeah, that's good.
Yeah, yeah. So, but that's a special feature of this model. It's not generally true. So there's a background density that we have to worry about, and that gives you this extra phase factor. And this is, you know, in the condensed application, this is absolutely crucial. Without this, you would just get the wrong type of spin liquid. All right. Okay, I'm almost done with this. So finally, the E particle moving around the M. And this phase factor, the M particle picks up around the lattice site, and the M particle moving around, I can also form the epsilon particle. So, which is the final thing I need to do to complete this description. So now the E particle and the M particles are present, perhaps in some world, or by tuning the couplings between them, they can form a bound state, and that bound state is called the epsilon. E and M. Okay, so here's an EM bound state. There's another EM bound state. So these have branch cuts. Let's say they go around this way. And now you can ask what happens when you move this bound state around the other one. So you take this particle here, this bound state, and you move it here. And that corresponds to an exchange of the two of them. Okay, so as you're moving this, sitting here, it's got this branch cut going out. And that branch cut is going to cross the E somewhere. And so this tells us that you're going to pick up a -1 as you move halfway around. Okay, so -1, this process leads to a -1, and that implies the epsilon is a fermion. And since the M has spin 0 and the epsilon has spin 1/2, this also has, in this case, spin. It's fractionalized and has spin 1/2. So I started with theory with just ordinary spins, and I wrote it in terms of these Schwinger bosons. And then I found saddle points. I found these non-trivial saddle points for the ends. I had an S particle, an M particle, and now an epsilon particle. And this epsilon particle is a fermion. So I've got a fermion out of just bosons all the way through. So that's also quite remarkable. Now, what's been done since then, especially some very nice work by Ashwin Vishwanath, is that this epsilon particle is in fact nothing but the Schwinger fermion, which we're going to play a lot with in the next set of lectures. In other words, instead of writing the spin here in terms of Schwinger bosons, I could also have written it. I could have done the same. I could have taken the same model and then a different mean field theory, where I've written S as some fermion f dag I alpha sigma alpha beta over 2 beta. So I get two different descriptions of the same Hamiltonian. One with bosons, spin 1/2 bosons, and the other with spin 1/2 fermions. Then I work very hard with these two descriptions. I get different saddle points. I figure out all the quantum numbers of the E, the M, and the epsilon. This is also turns out to be exactly the same structure, but you have to just replace bosons with fermions everywhere. So I get two different saddle points with all kinds of the same quantum numbers of topological quantum numbers, the E, the one, the E, the epsilon, the M. But I also have to look at various other symmetries like translational symmetries, lattice rotation symmetries, parity, time reversal, and so on. And in many cases now there's a classification that these are actually different descriptions of the same theory. You can start with theory with the epsilon particle, or you can start with theory with E particle. You end up with the same theory. Of course, one approach may be better than the other, depending on which is the lower energy excitation, or whether this bound states even exist in principle or not. Yeah.
For this equivalent, are you assuming that for the bosons you had one boson per side, so that orange S on the right corner is?
Yeah. So again, you also have the same constraint on the fermions. In this case, it's only work for spin and a half.
Yeah. Okay. Yeah.
You have to put more colors on the fermions to get higher than other spin.
Right. But then you would have other degrees of freedom.
Yeah, but it's still, I'm pretty sure it's possible, even for higher spin, to map boson theories to fermion theory. So this is a simple but proven example of fermion boson duality in 2+1 dimension, where it's not completely proven, but it's very, very plausible. There's a few things about the spectrum of the M particles that haven't really been matched, but we fully expect them to match. Where you can start with a theory with either bosons or fermions, but fortunately, you end up in the end with the same state in some invariant sense. And this is very nice because in the early days of studies of thin liquids, there were a lot of arguments between people using this point of view versus this point of view. And so we know that in most cases, they were talking about the same thing. All right. Okay, so that's my very sketchy approach to just showing you how you can, at least by waving your hands quite a lot, do that path integral over Q and how you get all the structure. But I want to do a little better. Now, of course, that path integral is really complicated, so we're going to have to simplify life a little bit and write down some simpler model, which we hope will capture all of the same physics. And there's a lot of evidence that it does. And the purpose of doing this a bit better is all we have shown here is the stability of this C2 spin liquid. It seems to be nothing dramatic going on. You've got some new particles around, but nothing has really destabilized the ground state. But eventually, as the fluctuates, as you get lots and lots of M particles. So let's imagine a situation where you get M. What does the M particle correspond to? The M particle corresponds to a flip in sign of Q across a batch cut. So as you're getting lots and lots of M particles, then you're getting lots of these fluctuations, this flux, this pi flux associated with each M particle is obviously very detrimental to the original saddle point. So eventually, when the density of quantum fluctuations of M particles become very large, you can imagine that there is a transition to where the flux is not well defined. Flux fluctuates so strongly that you get what's called confinement. So that's what we want to describe now, is the confinement transition of this phase of matter. Okay. All right, so we have this path integrals of Q's and lambdas to do. And what we want to approximate it in a way that preserves all these saddle points. At least the saddle points, the set of saddle points is the same. And we also want to, but the actual tunneling matrix elements may change. But of course, no problem, we haven't computed them anyway. We want to preserve the set of saddle points. And we also want to preserve this property, that every time an M particle moves around side, it picks up a Berry phase of -1 to the 2s. Okay, so we want to write down some simplest theory which have these features, the same set of saddle point and the same Berry phase. And we're going to imagine that the E and the epsilon particles really high energy, Those we don't worry about, they're gapped. But the M we want to worry about because it's only the M that destabilizes the original saddle point. Yeah, right. Introducing all these fluxes that weren't there to begin with. Okay. So the approximation we're going to make is we're going to replace each Qij by a new variable, which I'll call sigma Zij, which will be plus or minus 1. So, and the reason is obvious. I mean, everything we had to do with the fluctuations of Q and the creation of M, the most important thing they did was change the sign of Q, at least out here. You know, what's happening in the core, we can't capture, but we give up on that. That only happens in some small region. So let's try to forget about that and just keep track of the sign of Q. All right. So now you had a gauge symmetry. We want to keep that. So the gauge symmetry now will be sigma Zij goes to sigma Z ij times, I forget what I used in my notes, zeta I, zeta j, zeta I is plus or minus 1. So whatever theory we write down for these sigma Zij, we should be invariant under this very simple gauge transformation. This is therefore a Z2 gauge theory. Just as U1 gauge theory changes things by phase, here we're making life simple by just restricting to Z2's part of it. And the ultimate justification is that all the interesting saddle points that we're interested in only had a change in the sign of Q, far from the core. Or in the torus that was also explicitly true everywhere. So we just focus on that part that has all the interesting non-local structure that we are interested in. And all the other fluctuations, the phase of Q, and so on, they all seem to be gapped, like the spin-ons.
Sorry, can you repeat again? Like this gauge transformation, you're imposing it, you're deriving it from the Q?
We're going to write down some action for sigma Z now, or in fact, a Hamiltonian. And that Hamiltonian better be invariant under this gauge symmetry.
But why specifically this gauge symmetry is the angle? Sorry.
Well, once we restrict Q to be real and just equal to plus or minus 1, then the original gauge transformation, which is Qij, went to Qij e to the minus I rho I plus rho j. So there's still some life left in this because rho I can be 0 or pi. So just as I restricted Q to be real, then I'm forced to restrict rho I to be 0 or pi.
You're squeezing it on everything on the real axis.
Yes, so this zeta I is just e to the I rho I. And all the others Q's we assume need to get. But we have to keep track of the Z2 part because that's what appears as a flux in the Vizon. Okay. Then what about, so there's the sigma Z, but what about some actual quantum mechanics? Things are going to fluctuate. Let me delete this here. So another term in the action that I haven't at all mentioned so far, but would be needed to compute some of these instantons. For each Qij, I had an action. I'm now going to assume Q is real. Something like this. Just for ij side. This is my Lagrangian V of Qij. So this particular action, has we assume the magnitude of Q takes two possible values. So we rescale the Q so that this is Q equals +1 and this is Q equals -1. And this is V of Q. So we rescale Q so that there's a minimum here at +1 and minimum here equals -1. And that's of course what's measured by sigma Z. So there's some, okay. I have these two possible states I have to keep track of. But what I just told you earlier, there's also a tunneling between these two. So there's a tunneling operator that can take you from here to here. And that instanton, the effect of that, you compute from this kinetic energy term. So there'll be some splitting. And I'm going to call that splitting 2G. Okay, so the only thing I want to keep track of again is the fact that this sigma z can flip back and forth. And if I just had one bond, it'll cost me energy 2G. All right. Okay, so now we're almost ready to write down our rather drastic approximation to the original path integral over to Q. So we're going to say that there's a theory here, H equals, well, so we want a potential energy term. So we already had a potential energy term, which is product of Q around closed loops. So we just take the simplest closed loop. And I'm going to put things on the square lattice now, but you can put it on any lattice. So it's minus K. And product, let's say on L belonging to a square, because I'm on a square lattice of sigma z L. So this is just product of Q and Q star that I had before, and I replace Q by plus or minus 1, and just keep the very simplest loop, not all of them, just the simple one, and there it is. Okay. And then I have this thing fluctuating back and forth. That's going to give me some quantum mechanics with split. This will be energy G. So that'll be minus G on every link of the lattice. And I'll put a sigma X operator with someone else. So that's my Z2 Gauge theory, which I claim has almost all of the features in terms of the structure of its saddle points and the tunneling between the saddle points as the Q lambda path. It's simplified a great deal. This is the main simplification we made. This is really the only quantum tunneling process you're accounting for. Nevertheless, you'll find this is sufficient. Now, this Hamiltonian is sufficient to even make the Wigons move around. And in this particular Hamiltonian, you can even compute the energy and the mass of the Wison and everything in certain perturbation theory.
X gauge invariant?
Yes. So sigma X is gauge invariant object. Yes. So I've chosen a gauge. So this thing, this is only invariant under time independent gauge transformation. So I picked a gauge where I've fixed everything in time. And so you just rotate this qubit by 180 degrees about the x-axis. So that's the gauge transformation that leaves sigma X in there. So if this is Z and this is X, you perform an SU2 rotation where this goes to minus Z. So you rotate by 90 degrees about this axis. Nothing happens to X. So sigma X is invariant. So there is a unitary transformation. This is a unitary transformation. So let me write it out here. Sigma X on Ij goes to sigma X. This is the gauge invariant structure of the theory. It's invariant under this transformation. And this is unitary because you can perform a rotation of 180 degrees about the x-axis. And sigma z will go to minus sigma z, but sigma x won't change. Sigma y will change, but there's no sigma y in the Hamiltonian.
Excuse me, sir.
Yes.
So we are ignoring the lambda terms because it won't be what you say, not it's gauge invariant, but it would be a constant like term.
Yes, I've chosen a gauge where I don't worry about lambda. But that's actually a very important point. I'm now going to worry a little bit about lambda because it was the fluctuations of lambda when you perform them exactly that gave you this constraint of S dagger S equals 2S. And that gave us this constraint here that the motion of M around the lattice side picks up a Berry phase of minus 1 to the 2S. Okay, so I'm just going to give you state a condition, and maybe certainly next time we'll actually do a computation and verify this. Okay, so now let me just give you a condition. So this particular Hamiltonian has what we call as a Z2 gauge symmetry. Another way to say that is got an infinite number of conservation laws. There's an infinite number of operators that commute with the Hamiltonian. These are the gauge charges, or this is something called Gauss's law in electrodynamics. So the analog of Gauss's law is the following statement. So for each lattice site, there's a site I here. Notice these qubits of the sigma z variables are sitting on the links. So I have sigma here, sigma here, sigma here, sigma here. So these are sitting on the links. So for each lattice site I define the following operator. This product on L belonging to I, meaning that L ends on I, of sigma xi, of sigma xl. So I pick a lattice site, and I take the product of sigma x around on that lattice site. If I was doing this in a U1 gauge theory, I'll get the exponentials of the electric fields, and this will be the divergence of the electric field, gives you the charge. So this is the gauge charge, which is this sigma x, measure the Z2 gauge charge. Okay, so now this operator commutes with this Hamiltonian. Again, very easy to check. First of all, most importantly, of course, it computes with this. But why does it commute with this? Because sigma z does not commute with sigma x. So now the important point is that whereas sigma z does not commute with sigma x, it does anti-commute. Sigma z, sigma x is minus sigma x, sigma z. So if I take this loop, this packet here, and at this one, so this is my plaquette. And so I'm going to take product around this of sigma z on this plaquette. Or you can take, if it was a plaquette far away, of course it commutes, but this is the only dangerous one. And now what you notice is that this sigma z anti-commutes with this sigma x. This sigma z anti-commutes with that sigma x. And therefore, this whole thing commutes. So you can just check that GI commutator of the Hamiltonian is 0. We have an infinite set of conservation laws, which corresponds to an infinite set of Z2 symmetries, these 180-degree rotations. And that's what we call a gauge symmetry. So there's a Z2 gauge symmetry. These are the symmetry transformations. And they lead to an operator that's generated by this G, which commutes with the Hamiltonian.
This only works on the square lattice?
No, it works on any lattice. Yeah, everything I'm going to say will work on any lattice.
Because if you had a triangle plaquette, then you'd have 3 minus sides, right?
It doesn't matter as long as the, if it's a closed loop, it's going to go through this any lattice side an even number of times. You only care about these two ones. In the original theory, I had only even numbered loops, but this I could even put it on a triangle with odd number of loops, it still work. Yeah, take on any lattice. As long because a closed loop, if it's a closed loop here, it is always an even number of links ending at every point on the loop, even though the total number of links may be odd. Okay, so this is, it's got an infinite set of Z2 gauge charges. So now if this is operators that commute to the Hamiltonian, I have to tell you what the value of GI is. I have to give you the value. It's not something I can determine priori. There's a set of Hilbert, there's a Hilbert space here, and a spectrum of the Hamiltonian for each values of GI. And of course, the square of this is 1. So we know the eigenvalues of GI plus or minus 1. So I have to tell you for each lattice side, what is GI? Is it plus 1 or minus 1? And if you give me some set of gauge charges, I'm going to get a different spectrum for this theory. All right, so I'm not interested in any general gauge theories, so you could study it for general GI. I'm interested in this particular Hamiltonian. Okay, so now what we notice is that, what do we have? Yeah, okay. Yeah, it's not obvious yet. I will show it eventually. So we have exactly two S-gate charges, electric charges on each lattice side. And there are no electric charges in the Hamiltonian yet. Yeah, maybe that should be the next step. But let me just state the claim. So the claim is that GI on every side for the antiferromagnet must equal -1 to the 2s. So this is a faithful effective theory, which really gets, captures essentially all of the correct low energy properties of the Z2 spin liquid, and also the nature of its phase transitions into confining phases. That's also correctly captured by working with this very much simpler theory. This is the Hamiltonian. This is the sector of the Hilbert space you should work with. It should be exactly, for half integer s, it should be exactly one Z2 gate charge in the background. All right, let me motivate this a little bit. Let's try to put back these S particles back into the theory. So how do these S particles, if you want to really worry about them, if you threw them out, step one, with a big gap, but suppose I wanted to put them back in, how will they appear? Well, we already know how they appear in the original theory. The Hamiltonian for the S particles was Qij star, over all bonds of epsilon alpha beta, Si alpha, Sj beta. So what all we have to do is just replace this Qij by sigma Zij. Here we have it. And you also see from here that the S particles, Si alpha, under a gauge transformation, go to zeta I times Si alpha. So this kind of field that has only one zeta transformation is called an electric charge. So the S particles carry an electric charge of zeta I. So you can define, if you want to really have the G commute with this term, you have to add another factor in the G, which does this rotation. Okay. So I won't write that out, maybe because I haven't done it, maybe I'll do it by next time. So the G has to be modified, so it will commute with this term too. And the G should be such that it performs this particular transformation of the S. And so then you see exactly why this has to be -1 to the 2s, because under a gauge transformation, we know that there are exactly 2s bosons on each side, and each pick up a factor of -1. Okay. But the way to really prove it, according to things I put on the board, is to find the M particle excitations of this theory and have them do a closed loop on the square lattice. And you'll find you pick up exactly the -1 to the 2s factor. Okay, I think there's a good point to pause. I won't go over today. We ended a bit early, or open it up for any questions. So just to summarize then, we started with a generic set of Hamiltonians on the square lattice or triangle lattice. And under assumptions on the structure of certain saddle points, we've argued that provided the spin-on gap is large, that's really the main expansion parameter here, there is a very interesting ground state with fourfold degeneracy. And then fluctuations, gauge fluctuations about that ground state are described by this very simple theory with this constraint on the gauge chart. I should say this theory was first written down in this form but not exactly this form, in a space-time form by Wegner. This is Wegner's Eisengage Theory. That was 1975, a long time ago. He didn't have this anomalous gauge chart in the background. This was the original model for confinement in QCD. That was his motivation. But what Wegner was describing, and this wasn't something he was aware of in those days, was in fact a topological phase of matter with these fourfold degenerate ground states and all these other properties, the 1, the E, the M, and the epsilon. All of that in principle could have been worked out. Maybe it were worked out in those days by various people. But this part is new. That's also needed for a full theory of condensed matter systems. Okay, any more questions? All right, I'm sure you're all exhausted like me. So I'm going to end early today.